Hello and welcome to today's Nordic Tech webinar. The topic that we have for you is designing secure IoT products. And as you know, security as a whole is becoming increasingly more important for all sorts of embedded devices, and especially, of course, for IoT devices. I am your host for today. My name is Tiago Montt, and I'm a developer marketing manager here at Nordic Semiconductor. My focus is on developers and ensuring that they have everything they need to create innovative and, of course, secure IoT products with Nordic's NRF Connect SDK. Before we get started, a few practicalities. The webinar has a duration of 45 minutes, followed by a 50-minute Q&A. We, of course, highly encourage you to ask questions, but please type them on the top right sidebar. All the questions are anonymous, and please try to keep them relevant to the topic that we have today. We'll answer those questions towards the end. Then on the bottom right, you'll find a chat, and that is not anonymous. It should not be used for questions, but of course, you are encouraged to chat with the fellow attendees. And if you have more questions after the webinar, or if we don't get to answer your questions, then do go to the dev zone and get your questions answered there. And we'll have a recording of the webinar will be made available together with a presentation at webinars.nordicsemi.com/on-demand. So our agenda today is, of course, all about security. And we're going to take a top-down approach here. So first of all, we're going to talk about the why. So why is security so important? And then how is this approached for IoT? And then what is actually used then to ensure that you can deploy secure products, especially using the PSA certified IoT security framework. And many customers still ask the question why when it comes to security. Why is security important for my IoT device, for my IoT application? And not just today, but also why is IoT security becoming increasingly important as more and more devices get deployed to the field on the worldwide scale? Thinking a bit historically, embedded security is really nothing new. And there are some categories of embedded devices that have been very, very security focused from the get go. And two of those examples are SIM cards for mobile phones, as well as payment cards. So these types of devices and technologies have had very tight security requirements from the beginning, which ensure that all of these devices have a very high security baseline. However, unfortunately, there is also a vast array of other devices that have not taken sufficient precautions when it comes to security. And this is especially true with IoT devices. And the reason is that they offer a larger attack surface compared to non-connected devices, which means that the security bar needs to be lifted even higher. So security incidents with IoT devices are still quite much of a commonplace, and they can have wide-ranging consequences from data leakage that may reveal private information to more critical consequences, such as potentially loss of life when compromising certain types of medical devices. And the impact of these attacks and these breaches is very felt on the consumer confidence, which can decrease very heavily, and not just for the one device or the one brand that gets affected, but effectively for the entire product category of affected devices. And a good example of that are, all sorts of cameras, so video conferencing cameras, simple domestic surveillance cameras. And the challenge here is that as more and more devices come online, then this already large attack surface gets even larger. So, which means that the risk also increases with that. And One of the things that customers typically associate with security is cost, that it costs to implement security, to add security to my device. And that is true. The security does, implementing security does have a cost. But the flip side is that insecurity can cost even more. And some data here from the PSA certified 2022 security report, just to give a sense of scale of what it means to have insecurity on devices. During the first half of 2021, there was 1.5 billion attacks on smart or IoT devices. 1.5 billion attacks. And the estimates from various studies is that by 2025, the impact of cybercrime on a global scale is going to reach upwards of $10 trillion. And out of this, we know that a lot of IoT related attacks account for a significant portion of that total. But it is large numbers, and that we're talking about when it comes to security or the lack of security. And another very important topic within security is, of course, the regulations. And regulations, standard certifications tend to get used interchangeably, but they are different things, even though they are related. So, if we look at regulations first, one key takeaway is that they are mandatory and they are enforceable. And what this means is that if you want to go and sell a device on a given market, you need to comply with the local regulations for that market. Otherwise, you will lose access to the market and you won't be able to sell your products. And the regulations are developed by governments. It can be at the individual state level, or it can be at a higher level. If you think of the European Union, for example, which sets regulations that apply to all the member states. And regulations may rely on a standard, and then on the standard level is where the requirements are being defined. And the standards are optional. Many of them are a choice. They are created by standardization bodies. Two examples are the ETSI, which stands for European Telecommunication Standards Institute, which is an independent, not-for-profit standardization organization, or then also the NIST, which stands for National Institute of Standards and Technology. And that is an agency of the United States Department of Commerce. And standards may rely on either external or self-certification as evidence of compliance. What this means is if you think of the CE standard, that is a self-declaration standard. So device manufacturers will need to test their devices against the CE standard, and they will have a self-declaration that they comply with the standard. And then lastly, you have the certifications, many of them also optional, and they are usually awarded by private organizations. And within security, a good example is the PSA Certified, which gives out certifications against various levels of security robustness. So what you would do here is that you would take your device to a certified test house or a lab, and they will test your device against the requirements for one of these security levels. And then once you have a full pass, then you would get your certification as being compliant with that security level. And the regulation landscape is quite varied. It depends a lot on the product categories. So, for example, if we think about mission critical devices like medical devices, which of course can impact people's lives, and they handle sensitive patient data. There we have a high level of security in terms of requirements, so the baseline is really high. But then maybe on the other side of the spectrum, if we think about consumer IoT, there what is lacking is that there is no mandatory baseline. So there is no mandatory security requirements, and it's really left to the individual device manufacturers to assess and evaluate how much security they need for their products. But what happens commonly is that security is not tackled early on in the design phase. And then, of course, the result is that you have out in the field devices which do not have at least a minimum security level to protect against the threats. But this situation with a lack of baseline security requirements on some product categories is changing. So the regulators are catching up, and steps are being taken towards a future where the product manufacturers will be required to meet a baseline product security for market access, meaning that if the devices that they are manufacturing, developing and manufacturing don't meet those requirements, they will lose the right to sell their products across various markets worldwide. Worldwide. And as of now, the process is a little bit fragmented on a global scale, but it's underpinned by many common requirements. So in Europe, we have the EU with the Radio Equipment Directive, Delegate Act Article 3, which is one of the most important ones. And we have EU Cybersecurity Act, EU Cyber Resilience Act, and then we have in the UK Product Security and Telecommunications Infrastructure Act. In the US, for example, cybersecurity labeling for consumers, IoT. And then in other parts of the world, for example, in Asia, Singapore has the Singapore Cybersecurity Labeling Scheme, which is voluntary. And Finland was one of the first ones to have a cybersecurity label, which is also voluntary. But even though it's fragmented, for example, Singapore and Finland have bilateral recognition of these labels. So if you were to meet the requirements on either one of these countries, it would be recognized in the other one, and vice versa. And then also Australia has the Australian cybersecurity label that is currently being proposed. So now that we've talked about why it is really important to implement security, to take security early in the design phase for an IoT product, we're going to move now to how to approach this. So how do we actually go about implementing security in our IoT devices? And it's good to recognize that an IoT device, the security state of an IoT device is not the binary concept. It's not that you have a device that it's either not secure or secure, because no product is 100% secure. As long as there's an asset which is valuable and there are threats against that asset, then if there's enough time, money, and motivation, then that system can be broken because the attackers will want to get access to the value in your asset. And a better way to think about security, which is not a binary concept, is really about sort of an analog scale, if you will. It's really about balance, and it's balance between cost on the one side. So cost can mean engineering hours, for example, development time. It can mean memory on a device. If you need a little bit more memory, you need a larger device, which will be a little bit more expensive. It might mean data consumption. Let's say on a cloud backend, for example, it might mean power consumption if you need additional computing for secure-related functionality. It may also mean secure production if you need to set up a secure manufacturing environment for your IoT device. And then on the other side, of course, we have the risk, and the risk is impact times probability. So if you have an attack, which if conducted has a high impact, like for example, say there's loss of confidential personal data, and it also has a high probability because it's simple to conduct, then the resulting risk is raised. So there's a higher risk, and you should really consider implementing more mitigations to make that type of attack harder. So in other words, to reduce the risk. So it's really about balancing this between costs and risk, and depending on the product, because there are no two products alike. Each product will have its own unique requirements, and each product will need to implement the security which makes sense for the product, given the risk associated with that and the cost as well. But even though security is a balance, it should not start from zero. There has to be a baseline that already provides a robust level of security. So there's a few simple objectives that every product should really meet, and we have outlined 6 of these objectives that we'll now go through. So the first one is secure boot and secure update with anti-rollback. So what this means is that when the device boots, it can verify that the firmware installed on the device is authorized, and it can actually run. And then also that updating the firmware, which on IoT devices, that's typically done over the air. That is also done in a secure way. And additionally, the anti-rollback is a mechanism that aims to prevent an older version of the firmware to be reinstated. Because if we allow that, it could expose security issues that have been fixed on newer versions. And then another objective is isolation between secure and non-secure environments. So this means that within the device, there's a secure environment where the security services are running, and they are exposed to the non-secure environment, which is typically the user application, through APIs that abstract away the secure data. So they do not reveal any information about the secure environment itself. If you think of cryptography, for example, the non-secure environment would request cryptographic operations from the secure environment through these APIs without actually having any access to the keys or the underlying cryptographic implementation or any other resources that are reserved for the secure environment, and thereby making it isolated away from the non-secure environment. And then another objective is, of course, having secure storage for keeping security critical data and assets. And this, by this making it harder for that information to be compromised if there's an attack on the device that tries to gain access to that security related information. And then another objective would be attestation and unique identification. So this is analogous to how every person can identify themselves to prove who they are with a passport. So there's a similar concept on IoT devices. So devices need to provide evidence that they are the devices that they say they are. And of course, the goal here is to prevent illegal devices or unauthorized devices to be commissioned into a network where they shouldn't be. And then we have security lifecycle. So devices go through different states from production, debugging, of course, commissioning, all the way until they get disposed and we need to decommission them. And it's important that security is taken into account throughout all these steps on the lifecycle. So we have the security lifecycle as being part of the overall device lifecycle. And lastly, of course, cryptographic services. So the ability to run cryptography on the device, but in a way that the key information is not exposed to the application so that it can be accessed by an attacker. And now we move forward to the what. So what do we actually use as a guidance, as a framework to implement security in IoT devices? And this in this section, we're going to talk about the PSA certified IoT security framework. And for those of you who might not be familiar with the PSA, it stands for Platform Security Architecture, and it offers a standardized approach for securing connected devices. And this is from the initial security analysis all the way to the certification phase. PSA Certified is it's a global partnership of security conscious companies, and they are proactively building security best practice into devices at scale, so that it's one of the fastest growing and one of the most valued security ecosystems globally. This was originally spearheaded by ARM together with a group of world-leading security evaluation laboratories. So the challenge here has been that security within the IoT industry has historically been quite fragmented. It lacks a common language and standardized processes, implementations, as well as certifications. And as a result, it's been leading to very inconsistent and mostly inadequate levels of security across various devices. And from a product developer perspective, security was seen as something complex and it's an expensive process. The impact would be on the time to market, increasing time to market, and that could actually negatively impact the business. Although, as we have discussed, that is not quite the case, and it's really the lack of security that might have the highest impact from a business standpoint. So that is really the challenge that the PSA certified IoT security framework is aiming to solve, and it's doing so by offering a standardized approach to creating secure IoT devices. And this is from analysis through security assessment and all the way to certification. And if you visit PSA certified website, you can also find many free resources and training material. And that will help educate product developers on various security topics like threat modeling and certification. So this framework divides security design into a simple 4-step process of analyze. So that means looking at threat models and security analysis, to the architect. So looking at what you need from hardware and firmware to specify those two components. And then the implementation. So the firmware source code implementation. And then the certification step, where you go and take your device to be independently tested by a test house. So the first step in this process is the threat modeling and security analysis. Within threat modeling, there's essentially 4 sub-steps that we need to go through. And the first one is that we have to identify the assets that we want to protect against. So we might have keys in our device, we might have certificates, data, which we don't want anyone to be able to access. And once we have identified the assets, then we need to identify the threats. So the attack vectors towards the assets. So that could be an attack through the network. It could be an attack through the debug port, for example. So that's the second step is to identify the threats against the assets. So once we have those two known, then we need to do the analysis and prioritization. So we need to do a risk analysis. What is the probability of these attacks and what is the impact? And then we get the risk out of that. And once we have that, we of course prioritize the ones with the highest risk. Will be the ones that should be tackled first. And we need to look at the mitigation. So how do we actually control and implement mitigation against those threats? And if you look into the PSA certified website, you will find threat model and security analysis, a few examples available. So they are covering an asset tracker, smart water meter, network camera, and a few other device types. So if you search for threat model on psacertified.org, you will very quickly find these some of these examples. So let's look at an actual example of threat modeling. And the examples on this table were taken from a larger threat model, taken from PSA certified threat model training, for which you can find the link at the bottom of this slide. And this is for an asset tracker device. So the full spreadsheet is available on the link, and we took just some examples for this slide. So we have here listed the assets that we have on our device that we want to protect. And then we have the security requirements that we want to have on those assets. We have the threats against the assets. So we have the entry points or potential entry points of the threat, the impact of that vulnerability, the severity following the CVSS rating. So CVSS stands for Common Vulnerability Scoring System, and it provides a numerical representation from 0 to 10 of the severity of an information security vulnerability. And then lastly, we have the mitigation against the threat on each of the lines. So starting with the first asset, which is the firmware. The security requirement here is integrity. And the first threat that's been identified is to tampering with the firmware. So this is from a generic perspective, let's say firmware integrity that could be compromised by someone tampering with the device by, for example, installing malicious firmware, or also known as malware, over, for example, an insecure update service. So the entry point of the threat could be the malware, could be a bug, mass storage access, JTAG, network update. The impact is that someone could install the malware. And then we've also identified another threat being the escalation of privilege with the same entry points as the tamper threat. The impact of that vulnerability would be to launch a distributed denial of service, or DDoS. And the severity calculation for these is 9, so it's very close to the top of the scale. And then we have the mitigation against that. So the mitigation against the tamper would be the secure boot. So what this means is that if someone actually is able to install malware, if we have secure boot, then that malware wouldn't run. So they would be able to install it, but not to run it. So a device would not be compromised in that sense. And against the escalation of privilege, the mitigation will be to enforce the principle of least privilege. So to make sure that each of the layers in the software only has access to what it needs to run and nothing else. Then the other asset would be credentials. And the security requirement for the credentials is, of course, confidentiality. We don't want the credentials to be known outside of the device or outside of who needs to have access to those credentials. So the threat would be disclosure against tampering against the device to obtain the credentials. And the other threat would be the escalation of privilege. We have similar entry points to those threats: malware, bug, mass storage, JTAG, or using the network. And if there's a disclosure of the credentials, the impact of that vulnerability would be device usurpation. And if there's escalation of privilege, then the impact would be to modify firmware and install malware. And the severity calculation was 8.7 for these. The mitigation would be to have secure storage in the trusted execution environment. So having the data for the credentials would be stored in the secure storage in the trusted execution environment, making it harder for an attacker to get access to those credentials. And then the last asset, as an example here, are logs. So the security requirement for logs, there's actually two. There's integrity and confidentiality. And against the integrity, the threat of tampering has been identified. Against confidentiality, the threat of impersonation. Again, similar entry points, malware, bug, or access to mass storage. And in the case of tamper, the impact of that vulnerability would be the ability to suppress critical alerts and events. So that means that the device owner would lose visibility on what's happening to the device on the field if someone can tamper with the logs. And in case of loss of confidentiality, to gain access to system info. The severity calculation, is a little bit lower for these threats. And as mitigation for integrity, the recommendation is enforcing access control, and again the principle of least privilege. And against the impersonation will be secure storage in the trusted execution environment. So the next step after the threat modeling and security analysis is the architect. So we need to look at hardware and firmware specifications, which means that we need to select hardware and firmware, which allows us to implement the mitigations that we need to have in place to protect against the threats that we have identified on the previous step. So we need to look at the hardware and firmware that can support then the needs of that threat modeling. So let's say that we need, for example, hardware cryptographic acceleration. We would need secure storage, and we would need to implement isolation. So for the hardware, we would be picking something like the NRF 9160 or the NRF 5340 or the NRF 52840. So these are PSA certified SoCs, the 5340 and the 52840, and an SIP, system and package, for the 9160, which is a cellular device. So these are certified to meet security best practice requirements. So that's on the hardware side. Then on the firmware side, we would be using the NRF Connect SDK, which is the Nordic's flagship SDK for all of the products and all of the wireless stacks. And this would provide flexibility to the developer, enabling to implement the right security to be applied to the application, so that it can meet the requirements that come out of the threat modeling. And it also provides trusted Firmware-M, which is a reference implementation of the secure processing environment. Then we move forward to the implementations phase. So implementing the firmware for our application. And the user application would be interacting with the secure processing environment that runs on trusted Firmware-M using the PSA API. So these are standardized interface, standardized APIs towards security services. And they offer a number of benefits. So enhanced security, meaning that It enables devices, of course, to meet industry standard security, which is the whole goal of the PSA certified IoT framework. It is implementation agnostic, so the APIs will be always the same. So your application doesn't have to worry about the underlying hardware or software implementation or the differences between platforms, because the APIs provide that abstraction from the underlying hardware. It's flexible and scalable, and what this means is that it supports quite a wide variety of use cases. So it can be applied from very simple to more complex systems, still using the same API abstraction. And it's also future-proof. So the APIs, the PS APIs, have been designed to be updated because one thing is that security threats will also evolve. So we need to make sure that the APIs can be updated to evolve with them. And going a little bit deeper into Trusted Firmware-M, shortened as TFM. It's a reference or a secure processing environment reference, and it runs on TrustZone enabled hardware. TrustZone is ARM technology, and what it does is that it isolates then the critical security services and the data from the non-secure user application. So the user application interacts with the Trusted Firmware-M using the PSA APIs, and it doesn't have access to the underlying secure data. And it provides the PSA root of trust and the secure services implementation. Some examples would be cryptographic services, secure storage, or attestation. So a good example of the abstraction is that if the user application wants to request some sort of cryptographic operation with the PSA crypto API, that operation could be implemented using either hardware or software, depending what's available on the device. But that's something that the user application doesn't really need to worry about. It only needs to call the PSA crypto API, provide the data that it wants to encrypt, and say how it wants to have it encrypted. And it doesn't have access to any of the keys, and it just gets back the data encrypted using the underlying implementation without having to know any of the details. Going a bit deeper into TFM, here now we have an overview of functionality and the principles in TFM, and also the entire architecture and applications implementing TFM in NRF Connect SDK. So the main user application and libraries, which includes network stacks, middleware, as well as the Zephyr RTOS, are seen under the non-secure processing environment. Which represents the functional application firmware as we normally know it. Then we have the Trusted Firmware-M and bootloader components seen under the secure processing environment. And these are isolated from the non-secure processing environment and implement security critical functionality. The one thing is that there are multiple levels of isolation that can be achieved between these environments and also within the environments. And that's done through a combination of TrustZone and other hardware memory protection features. So the first level of isolation is the secure processing environment isolation. So that's isolation between the non-trusted world of user application and the trusted world of these security critical functions. Then we have a second level of isolation. So that's between the platform root of trust, where the security services are running. So that's isolated within the secure processing environment itself. And it's isolated from the application root of trust services. And those are application-specific services, meaning that they can be included if needed by the application. Some of these application root of trust services are predefined, such as the protected storage, but the application developer can also add custom application root of trust services if required for his application. And then finally, there's a third level of isolation. That one isolates the application root of trust services, not only from other parts of the secure processing environment, but also from other application root of trust services. And that really, in practice, what it means is that each secure partition is sandboxed, and it's only permitted to access its own resources. And now moving into the certification step. That is also the last step in the PSA certified IoT security framework. So the PSA defines 3 levels of certification from the silicon up to the end device. And at Nordic, we provide a silicon piece that is PSA certified silicon, implementing the PSA root of trust, which is evaluated by an independent third party. And then on top of the silicon, there is the system software providing functionality that will be utilized by the application. Nartos being an example of system software. And that will build on the PSA root of trust from the silicon to implement its own functionalities. And then finally, at the top level, we have, of course, the device, so the end device. That builds on top of both the certified silicon and the certified system software. And at this level, the certifications will align with the standards and regulations also for market access. And one thing that's really important to note here is that there is inheritance of certificates within the PSA certification scheme. So meaning that as a device manufacturer, if you select certified silicon and certified system software, you can inherit those certificates and evaluations conducted by the respective vendors when applying for your own PSA device certification. And that, of course, will reduce your own workload when it comes to device certification and accelerate your time to market. So to summarize on the certification piece here, so as we discussed, there's a PSA certified security certification for silicon, and then on top system software and end devices. And the two key takeaways here is that there is this is independently evaluated through independent labs. And then the other one is that it's a global certification program. So it's something that can be applied worldwide, and it's aligned with both existing IoT security standards, such as the ETSI EN 303645, as well as the NIST 8259A. But it's also aligning with other emerging ecosystems and labeling programs, so that it remains, a future-proof solution for customers who want to have their devices security certified. Nordic provides 3 devices that are PSA certified with the PSA root of trust. So the first device is the NRF 9160. This is a cellular device, cellular SIP module, offering LTM and NB IoT connectivity. Then we have our flagship NRF 5340. This is a dual core with 2 Cortex M33, and it supports Bluetooth Low Energy as well as 15.4 based wireless protocols such as Zigbee and Thread and Matter, which runs on top of Thread. So this is an SoC device. And then on the NRF 52 series, we have the NRF 52840, which also supports Bluetooth Low Energy and 15.4. So these are PSA certified level 1, which provides assurance of silicon implementing the hardware root of trust. They have been, of course, independently reviewed by a third party, by Security Evaluation Lab and a certification body. And this certification aligns with the latest baseline cybersecurity requirements, and also with the regulations with the mapping to the ETSI EN 3645 and the NIST 8259A. We're reaching the end of the webinar, and the key takeaway that we have here is that do prioritize security if you're developing IoT embedded applications. That is what we're doing at Nordic, investing in product security at the hardware, software, and services level. And as we've discussed early on in the webinar, the cost of insecurity can be higher than the cost of security, from business losses to many other potential negative consequences. So it's important that by prioritizing security, you consider it early on in your design. Do security analysis, do threat modeling, and go through the PSA certified IoT security framework, and use that as a guidance to implement security in your design. Because if it's not done early on, then of course, the later it gets brought into the design, then the more costly it will be, and it can of course have an impact not just on the cost of development, but also on the time to market of your IoT product. And to learn more from Nordic, we have, of course, our main corporate website, nordicsemi.com. But from a technical standpoint, the dev zone is where you can get direct technical support from our tech support team. So if you have any questions, we, of course, recommend that you search first to see if anyone else has had the same question, as that's often the quickest way to get support. But if not, then, of course, you can leave your own question, and our tech support team will help you get through any challenges you might be facing. Then we have the Dev Academy. So this is a online step-by-step guided group of courses, and we have courses on the NRF Connect SDK fundamentals, cellular IoT, as well as Bluetooth Low Energy. And we continue working on new courses to be introduced to the Dev Academy. So I really recommend that you check that out, whether you're just getting started or if you're already been developing with Nordic for some time. It's always valuable to go through that. And of course, then we have the Nordic Tech webinars, such as this one, where we cover a variety of topics, not as in depth, but still in a way that customers can get more informed about what Nordic is up to. So we have now reached the end of today's webinar. Thank you all for attending. And again, emphasizing that security needs to be taken early on in the design phase. Do get started with security today, and leave you here a link to the NRF Connect SDK documentation, the security landing page, where you can explore many other topics related to that. And now we can move on to the Q&A. All right, thank you everyone who attended. So we had a few questions coming in. Before we get to those, I'm going to just run a quick poll to gauge on satisfaction. So I'll start that now and leave it on for about a minute. And while doing that, I can start answering some of the questions. So there were a few questions related to roadmap, and we're not going to make comments related to our future plans. But the ones that there's, of course, a lot of them that we can tackle today. So the first one is asking, why are some labels voluntary when security is mandatory? So, and the answer is that so the different regions are for now having different approaches. So in some countries, the approach is to increase security level in IoT devices to introduce mandatory regulation. So it really enforces product manufacturers to raise the bar on IoT product security. In other countries, the approach is to introduce sort of a labeling scheme, and that also to help consumers understand the security level that the products provide, and allow consumers to choose and be informed with the information that they need to make these decisions. And some countries actually do both. So they have the mandatory baseline for security, but they also introduce labeling schemes so that consumers can make more informed decisions. And the other one, please comment about red cybersecurity and Nordic guidelines on this topic. So I added a few links to the chat for some PSA documents that talk about this, that provide guidance. So the Red Delegate Act Article 3, the detailed requirements are still in development. And the industry consensus at this point is that we expect that the requirements to be broadly in alignment with the at CEN 303645, which is the standard in the market today. And this standard maps to PSA level 1, for which we have the PSA level 1 silicon and root of trust certification for a number of Nordic devices that was discussed during the webinar. So the Nordic recommendations that you discussed with the lab that you're currently using for regulatory compliance, and the impact that these new security requirements in red will introduce. And there are two routes for regulatory compliance. There's a self-certification through documentation against the standard, or working with a notified body to gain approval. And your lab should be able to help you with this. So, but again, I recommend that you refer to the links that we added on the chat. But also in Nordic, we're also trying to create guidance for our customers when it comes to regulatory compliance. So you should see more content coming out in the next few months. And if you have any specific questions of course, DevZone is the place to go and ask them. Another question is, does the Zephyr boot have a signature mechanism to secure the firmware download? Does it use PKI to generate? So PKI is public key infrastructure. So MC boot can be configured to verify the signature of the application image updates before download. And you should configure it using your own keys. And those can be generated out of your PKI infrastructure. And then the other one is, does secure firmware update and anti-rollback takes into consideration of avoiding breaking the product during failed firmware updates? During development, testing, and evaluation, it may be necessary to install specific versions of firmware or rollback firmwares. How is the product implemented to allow these modes of operations? So anti-rollback, maybe this could have been a bit more clear, is that it's a generic recommendation. So in general, it's something that should not be allowed. However, there are these corner cases, like the ones that were stated in the question, and if it's authorized, then anti-rollback can be performed in those situations. And then, is TFM supported for NRF 52840? No, it's not supported on 52840 because it doesn't support trust zone. The M4 core in that device does not have the security extensions necessary to provide the secure, non-secure isolation. So TFM is supported on the NRF 5340 and the NRF 9160. And what parts of the SPE, so the secure processing environment, is open source? How is the NRF secure immutable bootloader provided? Source binary, which license? So MCU boot, TFM, and the secure immutable bootloader, they are provided as open source in the NRF Connect SDK. And I think that is now, I'm going to close the poll. Thank you all who replied to that. And yes, I think so. The last two questions that I see are, yes, well, we're going to share the slides. When the page for the on-demand webinar is up, there will be a link for the slides. Yeah, and I think that was the last then. So thank you all for attending, and we're going to be closing the webinar. Thank you. Okay, thank you everyone who attended today. We only had one question coming in. So before I tackle that, I would just like to run a quick poll so you guys can rate today's webinar. I'll let that on for a minute or so. And in the meantime, I'll just go through the question that came in. So the question was, you mentioned a key aspect of device security having anti-rollback. Is normal rollback still a desirable security feature? This is to handle cases where security issues are introduced in newer firmware. So the anti-rollback protection, that's recommended to so that you as a product developer to ensure that the older potentially insecure firmware is not reinstated. But for the case you describe where a newer firmware is actually introducing a security issue, then of course the strongest recommendation is that fixing the issue and incrementing the firmware version, so releasing a new firmware version with the issue fixed, or then updating. You can also update your old firmware as new firmware by incrementing the version number, and this is so that you can actually benefit from having that anti-rollback protection. Okay, I'll close the poll now. Okay, two more questions came in, so I'll answer those before we close the webinar. The one question is related to roadmap, if we are planning to certify any other part numbers. So that's something we don't talk about on webinars. And the other one is, how is isolation achieved with the NRF 52840 since it doesn't have trust zone? And the answer is that it does not actually support isolation. So as correctly stated here, it does not have trust zone, and the Cortex M4 also does not have the security extensions required to implement isolation. So isolation is actually only supported on the NRF 5340 and on the NRF 9160. Okay, so it seems that we're a bit light on questions, so I hope you have enjoyed today's webinar and have a rest of a good day wherever you are located. Thank you.